Hi, AP Calc BC students, Mr. Record here. Welcome to example 5 of our Lagrange without tears video series, right? This is going to be Lagrange error problem example 5. That's going to be another advanced placement style question. This one's going to involve a graph and will also probably be calculator active so that we can get this decimal answer. So without further ado, let's take a look at this. And so as you can see, we have a graph. So that's pretty easy to see down there. The problem says to let G be a function having derivatives of all orders for all real numbers with the graph of y equaling the absolute value of the fourth derivative of g of x shown above. If the third degree Taylor polynomial for g about x equal 2 is used to approximate g on the interval 1.5 to 2, what is the Lagrange error bound rounded to 3 decimal places for the maximum error if we wanted to approximate our g at 1.5 on that interval? So once again, as I said in example 4, which is sort of a sister problem to this one, is that the best way to get your foot in the door to start understanding the Lagrange error bound is to commit that formula right down there, right, that I'm partially covering up. Sorry about that. Commit that formula to memory and really be able to just basically regurgitate it, right? Just replicate it on paper. Hopefully then you can start filling in some of the pieces and then boom, all of a sudden your Lagrange error problem is going to be addressed. So what we're going to do is we're going to start off with this left side here. So we have the absolute value. Let's switch up colors. Let's go with a little blue here today. I'm feeling a little blue. You guys feeling blue? So we're going to take absolute value of our r sub n. Now let's think about this. We're going to use what kind of a polynomial? A third degree polynomial, it says. So that means r sub 3 is going to represent the error that we get. You might wonder, why do they use the letter r? It's a great question, but r oftentimes is called the remainder. And so if you take your approximated answer and add your remainder, that's your exact answer. That remainder often can be called the error. It's the difference between the actual and your approximation. So we're going to take that r sub 3, and it says we want to evaluate it at 1.5. So let's go. We're going to take the less than or equal, and then we have this giant absolute values here. And then notice up here, we're going to look at the maximum value of the nth plus 1 derivative of f. Well, in my problem here, the function's g. And so if we're looking at a third degree polynomial, we better be focused on the fourth derivative. And what a coincidence. Look at the graph that you were given. It is the graph of the absolute value of the fourth derivative. Oh my goodness gracious, things couldn't be any better. So we're going to do this at this z, the elusive z that sometimes we get a little bit too bent out of shape on, but you shouldn't, because this z, and if you saw in the previous video, sometimes I like to use a little notation down here at the bottom of my max just to remind myself that z, that middle thing is a z right there, is going to lie between 1.5 and 2. It's not something that's going to necessarily be provocative in this problem in that we're going to use that interval, but it's just a reminder about really what this Lagrange error bound is saying, is that we want this value z to stay in between there. We're not going to be able to find the exact value of z likely, but we're still going to be able to find what maximum it would produce. And so we will then finish this off by dividing by n plus 1. Again, that's our 4 factorial. And then over here, it says x minus c. Now, I want to be real specific here. My x is the 1.5. Now, I know that that can be confusing because you might be sitting there, you might be watching this video, and you might be wanting to say, wait a minute, Mr. Record, problem said that x is 2. Well, I know it did. But that's where we're centered, right? So we have to sort of read into that this 2 is really our C value. The X is always going to be what value you are trying to use to approximate, right? We're finding the value of the function G at 1.5, and we're using the Taylor polynomial to do so. So it's not too hard to get those two things straight if you think about it. And, the formula does say x minus c, and that's quite fine because, it doesn't really matter. If this is negative, it might be made positive by an even exponent, which in this case it is. But even if this power was odd, let's say that we were using a fourth degree polynomial and this was a fifth power, the absolute values are going to wipe away any negative that we have, right? We're just focused on a positive error, okay? So at this point, I think what we can do is find the maximum of that fourth derivative. Okay, where do you think that maximum is, guys? We're looking somewhere between 1.5, which is right there, and 2. If I look at the graph between, about 1.5 is the x value there, up to 2, what would you say the maximum value would be? And the answer would be 3. And it might be important that I underline those inequalities because we can achieve the maximum at the endpoints, and quite often that might be the case. And so we're going to use a 3 up here. Good for them. Good for them. So 4 factorial is going to be 24. 1.5 minus 2 rather is going to be a half, and that half is going to be raised to the fourth power. And if this was maybe a multiple choice question without calculator, that likely would be an answer option. If this is a non-calculator free response question, we really don't have any need to go any further. Being that this is a calculator active and they did ask to round to 3 decimal places, by the time we do that, and I will let you check this to make sure it's right, but you should get 0.008. Basically what that means is that if we use the third degree Taylor polynomial for g, and that is what's evaluating the 1.5 for x, we're going to get an answer that's only 8/1000ths off by the most if we use the actual function for g of x, which could often be depicted by an infinite number of terms in that Taylor infinite polynomial. So anyway, I hope this helps. We do have one more video, another AP style coming up in example 6. It's a little bit more proof oriented, a very common question that you're going to see on the BC exam in any given year. So you might want to check that one out as well. Anyway, I hope your Lagrange error estimate knowledge is being enhanced, and I want you to keep working and just believe in yourself that you can do this. We'll see you next time.